Take a look at the vector diagram that we have on the left side of this page. Is this a good vector diagram, by the way? All of these vectors that we're trying to draw, or sorry, that we're trying to add together are drawn head to tail. And they should be, right? They should be. So this is a good vector diagram. Now, we don't have the resultant vector there. We don't even have these labeled right now, but you can see the diagram itself is good. Let's make this 100 meters. Let's make this 75 meters at an angle of 30 degrees right here. And let's make this 100 meters as well. Let's find the sum of these vectors. Now, to find the sum of these vectors, I'm going to draw a resultant vector from start to finish, and it's going to look something like this. We can't find the value of that resultant vector right now because we don't have the goal. What's the goal? Right angle triangle. We don't have a right angle triangle. In fact, we don't even have a triangle. Looks like we have two triangles here, but don't even go there. Don't even try to deal with those two triangles, okay? It would just lead to heartache. Don't do that. Let's do what we do to find a simple right angle triangle. First thing we do, I got a funny angle there. What do we say when we see a funny angle? I don't like funny angles. So let's take this off to the side right here. Let's label my 30 degrees right here. Let's label this 75 meters. And then let's draw X and Y here. This is going to be X, and this is going to be Y. Which side of the triangle is the X component? Is that opposite, adjacent, or hypotenuse, Trent? Yeah, it's the adjacent side. So if we've got adjacent and we've got hypotenuse, we're going to use which trig function? Cosine, right. Cosine 30 degrees is equal to X over 75, adjacent over 75. X is going to be equal to, I don't know what that is. We're going to find an angle. We're going to use an angle trigonometry here. So what should we do in our calculator first time today? Yeah, let's go sine 90 just to make sure. Yeah, it is 1, so we're good to go. Let's say 75 cosine 30 gives me a value of 64.9519. Some of you might make that negative. Doesn't really matter right now. The y component is the opposite side, so we're going to use sine for this. Sine 30 degrees is equal to the y component over 75. That ends up being equal to 37.5 meters. Is this ringing a bell? Box this off. Okay, box this off because this is what makes this question different than the previous questions. Maybe I even want to do this. Maybe I even want to erase this. Oh, I guess I can't. Just replace it like this. Okay, this is 64.9519, and this is 37.5. And maybe I just want to scratch that out. Pretend it's not there. You can notice it there, right? But you know it's supposed to be gone. Okay? Replaced by the 64 and the 37. Now what? Now, sorry, what was that? Yeah, we have to do vector addition, but what do you mean by that? Like, be more specific. What do we mean by that? Emily, what do we do with our vector addition here next? Yep. Now we got to do all the x and y components. Good. So let's look at each of these vectors here. What's the x component of the first one, the 100 meters? Rochelle? Good. What's the y component of that, Rochelle? Good. Negative 100. Good. What's the x component of the second one? That's 75 meters that's dead to us. Lucas, what's the x component of that one? The 75 meters that's gone, it's dead to us. Yeah, except we're going to make it negative, right, because it's to the left. So negative 64.9519. What's the y component of that, Lucas? Good, 37.5. The x component of the last one, the 100 meters, is, oh, this one's easy, right? Marcos, the x component of this one is what? Good. And the y component is negative 100. Good. So we're going to add these up, negative 64.9519. Add these up, negative 200, negative 162.5. Is that right? And then we redraw it. How did we know to make this one to the left. How did I know to make that one to the left? Yeah, because it's negative and it's x component, right? How did I know to make this one down? Because it's negative and it's y component, right? Is this drawn correctly here, head to tail? Yep. The resultant vector goes from start to finish. Where do I label my angle? Position 1, 2, or 3? 1, 2, 3. Position 3, yeah. R is the square root of 162.5 squared plus 64.9519 squared. Let's figure that out. Let's square root that. 175 exactly? Oh, look at that. 175 meters. And theta is the inverse tan of opposite over adjacent. What's the opposite side here? What's the opposite side? Solana, what's the opposite side here? Yes, 162.5. And the adjacent side is 64.9519. And let's do that here. Second function tan 162.5 divided by 64. 68 degrees. What would we say? 68 degrees what of what? Where are we measuring that angle from? Let's draw a little crosshairs here, okay? Where are we measuring that angle from? Well, clearly it's going south and west, right? Is it measured from the west or is it measured from the south? Is it touching the south or is it touching the west? Marcos? Touching the west, so it's measured from the west. But yet we're going south. South from the west, or south of west. All right, if we're good with that, let's go on to the application of vector addition that we saw on Friday of last week, and that was relative motion. We saw last week that when we add vectors together, when we're finding relative velocity in one dimension, pretty easy. We still have to add vectors together, but it's pretty easy. Remember on that moving walkway that has a velocity of 3 meters per second this way, but yet I have the ability to walk 2 meters per second this way. If you're standing over there beside the moving walkway and you're looking at it and I'm walking on it, how fast am I moving relative to you? I'm walking to the left, the moving walkway is going to the right. I'm moving at 1 meter per second, right? My relative velocity is 1 meter per second. How do we do that? We added these vectors together. 3 plus negative 2 is 1. Okay, those vectors are easy to add together. We learned that in grade 4, grade 5, grade 6, something like that. Not so much, we didn't call it vectors, but we learned to add positives and negatives, right? 3 plus negative 2 gives me 1. Okay, not very hard. But when we have vectors in 2 dimensions where we want to find the relative velocity, okay, we have to use the vector addition rules that we've learned over the past several days. And that is the whole, remember the goal is to get a right angle triangle, do the Pythagorean theorem and the tan function, and so on. To do that, to make these questions that we see involving relative motion make sense to us and make the diagram easy to draw correctly, we usually break our vectors down into solid lines and dotted lines to make it clear. Our solid line vectors are going to be vectors that contribute to where I go. Okay, so solid lines contribute to where I go. Versus the dotted line vectors, which they don't contribute to where I go. These are where I actually do go. Does that make sense? So, for instance, if I gave you the velocity of the wind of 50 kilometers per hour, okay, I'm driving a car in the wind, or I got a boat going in the wind, or I've got an airplane flying in the wind, and I said that wind velocity was 50 kilometers per hour to the east, would that be a solid line vector or a dotted line vector? Solid, yes, because that's not where I go, right? I don't go in the direction of the wind. That contributes to where I go. Does that make sense? So we're going to make that a solid line vector. Wind. What else would be a solid line vector? Give me another example of a solid line vector, something that contributes to where I go. Yeah? Yes, a river current. If you're swimming across the river and there's a current that's coming to the south downstream, I don't actually go right across the river, right? The current contributes to my actual motion. Absolutely. What else contributes to where I go? Yeah. Yeah, where I head, where I aim, right? If I aim to the north, if I head to the north, well, that doesn't mean I go to the north, but it contributes to where I go, right? Another one we talked about, a little bit trickier, we say the airspeed. And along with airspeed, you know what that means, right? The airspeed is the speed that an airplane can go in the absence of wind. Along with that could be, well, a speed that a swimmer can go in the absence of a current, or the speed that a boat can go in the absence of a current, right? If a plane can go at 900 kilometers per hour in the absence of a wind, doesn't mean it goes at 900 kilometers per hour. You ever been in an airplane where the pilot says, I think we're going to make up some time here because we got a tailwind, right? You ever hear that? Or a headwind, it might take us a little longer, right? Okay, if the plane can go at, the airspeed of the plane is 900 kilometers per hour, and there's a tailwind, maybe the plane can go at 920 kilometers per hour because of that tailwind. Right? So the airspeed isn't where we actually go, it contributes to where we actually go. Versus our dotted line vectors, where we actually go, well, our actual velocity, or sometimes we call it the relative velocity, the velocity relative to the ground. Okay? We did 2 questions for homework on worksheet number 8. Let's take a look at both of those questions here now. Number 1 and 2. Except that's not the worksheet. There we are. Pilot heads her plane with a velocity of 250 kilometers per hour to the north. There's a wind of 100 kilometers per hour to the west. Holy cow. May I suggest to you, if you're flying in a plane small enough that it only goes 250 kilometers per hour, because that's pretty slow actually for an airplane. It has to be a small plane. You should probably not be flying if the wind is 100 kilometers per hour blowing to the west. Okay, that might be bad news for you. But let's assume that you are and that you're doing it okay. 250 to the north is going to look like this. Should it be solid or dotted though? Solid, because like this isn't where the pilot goes or the plane goes. This contributes, right? We're going to make that a solid line vector, 250. Now, we got a wind to the west of 100 kilometers per hour. Is that solid as well? Yeah, I don't go to the west, right? It contributes to where I actually go, right? Where should I draw that though? I'm going to give you 4 options. Okay, 4 options. Option 1, 2, 3, or 4. Where should I draw that 100? Where? How many people say number 1? Can I draw it in position 1? No, because that would be tail to tail, right? Can I draw it in position 2? Absolutely, that would be head to tail. Position 3? No, because that would be head to head. Position 4? Yeah, that would work. That would be head to tail. I'm going to draw in position 4. Okay? But if you want to draw in position 2, that would be absolutely fine. Just that the angle you'd get would be the complement of my angle. You guys know what that means? If I get 60, what are you going to get? 30. If I get 60 east of north, you're going to get 30 north of east, right? Make sense? Which should be correct. So I'm going to draw this. I'm going to draw in position 4 just because, I don't know, because I want to. And I'm the teacher, and I can do whatever I want. So it's in position 4 there. Those are solid line vectors. My dotted line vector, well, that's the resultant. That's the one that goes from start to finish. That's the relative velocity, the velocity that we're trying to find. That's the sum of the vectors that we've been doing for a week here now. Where am I going to label the angle? Position 1, 2, or 3? 1, 2, 3. Position 1. Good. Always at the start. R is going to be equal to the square root of 100 squared plus 250 squared. Anybody have a value for that, by the way? 269.3? And the angle, theta, is the inverse tan function of opposite over adjacent. What's the opposite side? Is it 250 or 100? Marcus, is it 250 or 100? Which is the opposite side? 100, good. Anybody have a value for the angle there? Should we expect that to be bigger than 45 or less than 45? It should be less than 45, right? What do we end up getting? 22? We should have 3 digits though, right? 22 point. If you look at your data here, this is 3 digits, this is 3 digits. Final answer should be 3 digits, right? 21.8. And how would we express that? 21.8 degrees, what of what? We're going we're going west and we're going north, right? But are we measuring it from the north or from the west? From the north. So we're going to call this west from north or west of north. How many people drew it the other way? Went 100 and then 250 up, and you should have gotten, what, 68.2 degrees west of north? Yep. No, sorry, it would be north of west, right? 68 degrees or whatever it was, north of west. Yeah. Good? Yep. I got west of north because my angle is drawn right here. If I draw the little crosshairs at the start, we can see that the angle is measured from, this is north, right? It's measured from the north. But yet it goes west from the north. So instead of saying west from the north, we're going to say west of north. Okay? Good. How many people got that one? Good. Let's take a look at the second one here. The airspeed of an airplane headed north at 40, wind at 15, blowing to the west. What's the velocity of the airplane relative to the ground? It's the same question, isn't it, pretty much? Different number? Yep. Oh, good question. Anybody answer that? The question, if you didn't hear it, was, why do we have to, in question number 1, why do we have to find the angle if the question doesn't ask you for the angle? It just says, what's the velocity? Because velocity is a vector, and vectors include direction, and the only way that we can express a direction is with the angle there. Make sense? So just like in those vector addition problems we were doing last week where we found the displacement, we said add the vectors together, but what we were really doing is finding the displacement. We found an angle because displacement's a vector as well, and we needed a direction. Okay, so 2 is almost the same here, guys. Airspeed of an airplane headed north is 40. That contributes to where the plane goes. There's a wind blowing to the west at 15. That contributes to where the airplane goes. And this is where the airplane actually goes. R is the square root of 15 squared plus 40 squared. Anybody have that? .43 degrees. 43 meters per second. And theta is the inverse tan of opposite over adjacent. Alex, what's the opposite side of this triangle? Is it 15 or 40? 15, good. So the inverse tan of opposite over adjacent, 15 over 40. Gives me 21 degrees. And what are we going to say that 21 degrees what of what? Right? Yeah, that would be west of north. West of north because it's going north and west, right? But we're measuring it from the north to the west. West from the north. West of north. Okay, I'd like you guys to take a look right now yourselves at your desk at questions 3 and 4 on that worksheet, please. Let's have a look at question number 3, everyone. Number 3 says a boat whose speed in still water is 2.5 meters per second. So in other words, this is how fast the boat can try to go. This isn't how fast the boat goes. This is, in the absence of a current, how fast the boat could go. So this is basically how fast the boat can aim. It contributes to the motion of this boat. This would be a solid line vector. The river is flowing at 1.2 to the south. That would also be a solid line vector. But the thing is, in question A and B, we don't actually have to even draw the vector diagram, because we're dealing with one-dimensional relative motion problems here. It's like the escalator problem or the moving walkway problem that we were talking about, right? Moving walkway is going one way at 3. I'm walking the other way at 2. All we got to do is add, right? Grade 5 rules of addition. Same thing with question 3A and 3B as well. If the boat is headed south, then we're going to say the boat, let's say north is positive, south is negative. Then the boat has a velocity of negative 2.5, and we add to that a velocity of negative 1.2, because the velocity of the river is 1.2. We're adding vectors together, whether it's one-dimensional or two-dimensional. It's just easier to do it here than it is to do it when we have a two-dimensional problem, that's all. Negative 3.5 plus negative 1.2 gives me negative 3.7 meters per second, or we could say 3.7 meters per second to the south. Makes sense? Boat's going 2.5 to the south, current's going 1.2 to the south. How fast am I going? 3.7 to the south. Got it? Now, question B, the boat is headed north. Well, this time we would say the velocity of the boat is positive 2.5. The current is still negative 1.2. So I end up going at positive 1.3 meters per second, which, if I define north as positive, that means to the north, right? Make sense? You're able to go at 2.5, but the river's kind of pulling you back at 1.2. You end up only going at 1.3 relative to the shore. Good? Now, question C, we're still adding the vectors in question C, just like in A and B, except in question C, because the boat is headed west, we got to draw a vector diagram. The boat is headed west at 2.5. There's a river current that's going at 1.2 to the south. Is that okay to draw like that? Yes, head to tail, right? Head to tail. Those are both solid vectors that contribute to where I go, and the actual velocity of the boat is this way. We're going to find R, we're going to find theta. Gives me 2.77, 2.8. And the angle, theta, is the inverse tan of opposite over adjacent. Tell me what the opposite side of this triangle is. Nick, what's the opposite side of the triangle here? Is it 1.2 or 2.5? Yeah, 1.2 over 2.5. We have to check the degree, the sine 90 thing again? No, we already did it once, right? We're good today. The inverse tan of 1.2 divided by 1.5. Is it over 2.5? Yeah. Good. 26 degrees. 26 degrees of what of what? Yeah, this would be south of west. Whoops. South full west. South off west. You know what I meant to do, right? Measuring it from the west, but yet we're going south from the west. Listen, you can see how maybe if you were the captain of a ship or the pilot of a plane, it might be useful to know a little bit of vector analysis, right? It might be useful to know where you're going to end up when you aim in a certain direction. One more example right now, number 18 for the unit here. This says a boat heads north across a river at 10 meters per second that's flowing east at 5 meters per second. Okay, the boat is heading across at 10 meters per second. Doesn't mean it goes north, it heads north. So that would be a solid line vector because it contributes to where I go. The river is flowing east at 5 meters per second. It contributes to where I go. What's the boat's velocity relative to the shore? Well, we've done that question, basically, right? We've done that question several times. We would say the boat heads north at 10 meters per second. There's a river current to the east at 5 meters per second. Both solid line vectors. The dotted line vector, which is the resultant vector, is the actual velocity. This is the velocity of the boat relative to the shore. I can find that. Here's theta, here's r. R is the square root of 5.0 squared plus 10 squared. And that gives me a value of what? That's 11.1. Let's just say 11 meters per second to two significant figures. Theta is the inverse tan of opposite of adjacent. Nothing new in this question, right? It's the next question that becomes a little bit more challenging. 27 degrees. We're going to say that's 27 degrees east of north, although you could have drawn it differently and gotten, what would it be, 53 degrees north of east? Both are correct, right? Good with that? Not too bad, not too bad. B, how much time does it take for the boat to cross the river? What? How much time does it take for the boat to cross the river? Well, you are missing a bit of information here. It should say that the river is 200 meters wide. There's no way you can figure out how long it takes to cross the river if you don't know how wide the river is, right? So the river is 200 meters wide. Let's label that. Here's my river. Let's label that not as part of my vector diagram, but just kind of off to the side. Anybody have an idea here as to how to go about this? Yeah. Yes, we could absolutely use the velocity equation. That's a great start. We could say V is equal to displacement divided by the time. And then we can rearrange that, get the time on the top. Okay, becomes V times T is equal to D. And then we take the V down by dividing. We get T is equal to delta D over V. Good? Absolutely. 100%. That's exactly how I would have started this. Good. Nick, what do you say? We should use the unrounded number. Yes. We probably should have written that down, but you'll see why in a minute, why I didn't record the 11 to more digits. But yeah, we should definitely use the unrounded number. Okay, what's the displacement across the river? 200 meters. What's the velocity across the river? 11, what was it, 10.9 there or something like that? What was it on my calculator? 11.18. Should I do that? 11.18? Hold on before you write that down. That's wrong. You cannot do that. You cannot use that 11. Well, actually, you could use the 11.18, but if you did, you couldn't use the 200. So you can't use them both. It's either the 200 or the 11.18. You understand that when I use this equation back here, this equation always assumes that velocity and displacement are in the same direction. Got it? If displacement is to the right, the velocity is to the right. If the velocity is down, then the displacement is down. Well, here I'm using a displacement straight north across the river, but I'm using a velocity at an angle of 27 degrees. Those aren't the same direction. What should I do here? If I'm using the 200 meters across the river, what should I use for my velocity? 10. Because the displacement and velocity have to be in the same direction. 200 divided by 10 is 20 seconds. It takes 20 seconds to get across the river. Now, some of you might say, well, why wouldn't I use the 11? You could use the 11, but if you use the 11 meters per second across the river right here, you'd also have to have a displacement across the river in the same direction, which would be different than 200, right? Make sense? Always make sure that displacement and velocity are in the same direction. If you use the displacement across the river, which is what I would do, then use the velocity across the river. If you want to use another velocity, that's okay. You just need another displacement, that's all. C, how far downstream does the boat end up when it makes it to the other side? Let's rearrange this equation again, solve for displacement, V times T. If I want to find out how far downstream it goes, what velocity should I use? 5, yes, use the 5 meters per second. Because if I want my displacement to be to the east, I need my velocity to be to the east. What time do I use? 20? Oh, do I have to find the x component of that 20? No. Your velocity and displacement have to be consistent, right? Look up here. 20 and 10 are both north. 5 and whatever displacement I get here are both east. Velocity and displacement have to be consistent, but time doesn't. Why not? Why doesn't time have to be the same? Because time's a scalar. There's no direction with time, right? There's a direction with displacement and velocity. They have to be consistent. Time doesn't. So we're going to say 5 times 20 is 100 meters, or actually 1.0 times 10 to the 2 meters. Again, if you're the captain of a ship, it might be useful to know not only where you actually go, what direction you go, but it might be useful to know how far downstream you end up when you hit the shore on the other side. Make sense? If I wanted to end up straight across there, then I'd have to aim up this way, right? I'd have to aim kind of northwest. I'll ask you to take a look now at your worksheet again. This time, specifically question number 5 on your worksheet. Same type of question. Exactly the same type of question. Just remember that you've got to be, for velocity and displacement, consistent. If your displacement is across the river, that's great. Use your velocity across the river. If your velocity is downstream, that's great. Use the displacement downstream. See what you can do with that now, please. Let's have a look at question number 5 here. It says, the captain of a ship aims a ship with a velocity of 2.5 meters per second directing north across the river, whose current flows at 8.0 meters per second to the east. The river is 850 wide. What's the velocity of the ship relative to the shore? How long does it take the ship to cross the river? How far downstream does the ship end up? So notice it's the captain of the ship aiming his ship, because he's aiming straight across and he ends up going downstream somewhere, right? You know that if it was the captain of a ship aiming her ship, she would have ended up in the spot she meant to end up, okay, because she wouldn't have been too proud to ask for directions if she needed it, right? The guy just ends up downstream somewhere where he's not supposed to end up, right? Because guys do that, right? Aims a ship 2.25 meters per second directing north. Is that going to be solid or dotted line vector? 100% solid, right? Current 8 meters per second to the east, solid or dotted? Is it? Solid, 100% solid. So we got 25 north, we got 8 this way. Those are both solid line vectors. My dotted line vector is right here. What's the value of R there? Who's got that? I want to say 26, 27. 26.2, okay, 26 meters per second. And the angle here would be the inverse tan of 8 over 25. I'm going to say like 30 degrees. 18, oh, not even close. 18 degrees, we're going to make that east of north. East of north. Okay, there's A, the velocity of the ship relative to the shore. What's the time that it takes the ship to cross the river? Here's the river. The river is 850 meters wide. Don't label that 850 on your vector diagram. Just label it kind of off to the side. What did we do? What equation did we use to find this? Yep, V equals D over T. If we rearrange that, we get T is equal to D over V. What displacement do you want to use? Well, we only have one, right? So let's use the 850. Maddie, if we're using 850 for displacement, what are we going to use for velocity? Yes, 25. Because the 850 is straight across, the 25 is straight across. 850 divided by 25, what would that be? 34? 34 meters per second? Sorry, 34 seconds, right? So my time is 34 seconds. How far downstream does the ship end when it reaches the other side? Well, again, we're going to say D is equal to V times T, right? If I want to find out how far downstream it goes this way, then what velocity do I need to use? What is it? 8, yeah. If I'm finding the displacement to the east, then I need to use the velocity to the east. 8 times 30, can I use 34? Sure. Times a scalar, doesn't really matter that we found that for the other component here, right? 8 times 34 would be, hold on for a second, let me figure this out. 8 times 34, 8 times 30 is 240. 4 times 8 is 32, 272. 2.7 times 10 to the 2 meters downstream. If you're trying to go straight across, that was not very good. Okay, we did not do a very good job of going straight across there.